The meeting is being live streamed. Okay, give me 10 seconds.
Exactly 10 seconds.
Oh, I think it's okay. It's okay now. Yeah. Then, okay, let me share slides and share screen. Share. Then I go to this and the slideshow. Slide. Show slide number. Play. Okay, play slideshow. Can you see my slide?
Yep.
Is that full screen or
no? Not yet.
No, yet.
No.
Oh, okay. Maybe play again.
Yeah, now it's full screen.
Okay. Okay.
Yeah, so welcome to everyone who's already joined us on Zoom and also on YouTube. So maybe we can also announce that you already got this email earlier today that we're hosting this special social hour tomorrow. So same time as now, but instead of a regular lecture, we're going to do a panel discussion on Zoom. And so this will be your chance to ask the organizers and the speakers about any questions you might have. It could be questions about physics, but also questions more broadly about careers and life as a physicist, or anything else you can think of. So it'll just be an open discussion, and we'll just be happy to answer any questions you might have. And for the second part of the social hour, we will move to a different platform called WonderMe, and there you can basically walk around in a virtual environment and interact in smaller groups. And this is supposed to be a more informal discussion where you just get to network and socialize with everybody else at the school. So we hope you will be there with a lot of questions, and we hope to talk to you all tomorrow more personally. So with that, I think we can start with the program today, right? Yeah, so our first speaker today will be Professor Nobuchika Okada from the University of Alabama. Nobuchika is, of course, one of our organizers as well. So he's been double tasked with organizing as well as speaking. And he's also, in addition to doing all these things, also running the YouTube live stream and setting up Zoom and doing all these things. So thank you, Nobuchika, for all of these.
You're welcome, of course.
With that,
my pleasure.
Now you can act as the speaker and teach us about freeze-in and freeze-out scenarios for dark matter.
All right, thank you very much, Christian.
Just a comment. Yep. Did it start the YouTube live stream already?
I think I already, I think so.
I didn't see it, so I just wanted to confirm.
Oh, really? Oh, okay.
On Zoom, it says live on YouTube.
It already says, okay.
Oh, it's okay?
Yeah, I think in that case, it should be okay.
Okay. Yeah, it says live. Okay. All right, so I'm supposed to give a lecture on the freeze-in and the freeze-out scenario. That's a very popular scenario for dark matter physics. All right, okay. So let me begin with introduction and introduction and motivation. And the first, let me begin with the what you already know, and the problem of the standard model. Well, this is the status of the current particle physics. And the standard model is the best theory in describing the nature of elementary particle physics, which is in excellent agreement with the almost all current experimental results, but including the LHC Run 2 results as of today. However, we know the new physics beyond the standard model is strongly suggested by both experimental or theoretical point of view. Here. Okay, so today I focus on the dark matter physics. And we have the one important problem, that's a cosmological dark matter problem. Right? We have now the CMB, the very precise measurement of CMB, and the Kobe from the WIMP and Planck. We already have the lecture on this stuff, related stuff. And so now the observational cosmology is actually a precision science. You can see that the COBEs and the that's the anisotropy measurement and the temperature measurement of the cosmic microwave background, and starting from the COBE, and that's a satellite experiment, and the WMAP, and then now Planck, and that's a Planck 2013. So now we have the latest data 2018. You can see that the dramatic improvement of the resolutions. So now this, well, we have a very precise measurement of the cosmological parameter from this CMB measurement. There, that's actual CMB spectrum fitting. Okay, yeah, okay. So then we now know existence of dark matter. And so that has been, existence of dark matter has been established. This is the energy budget from the of the universe, and precisely this is precisely determined by the WMAP and the Planck. All right, so we have the we already discussed this before, and in this score, and the dark energy, the almost 70%, and the 27% from the dark matter, and a known particle part, the known matter part is only 5%. Okay, so the most of the energy budget, the universe, is from the unknown state, and I focus on the dark matter today. Well, this is also the yeah, I can skip this one. So we have the other evidences of the dark matters, and the rotation curve and the Barrett cluster and so on. So I focus on the dark matter problem today, and that's one of the major problems, the standard model. So here is the basic properties of dark matter. Well, normally we think so, and this is non-baryonic. Not this means they are not the ordinary matter, and that's electrically neutral. We say dark, right? Might have a charge, but that charge must be really, really small. And also they are stable. Dark matter exists. Dark matter is out there. So, and that must be the stable particle. At least the lifetime of the dark matter, and longer than the age of the universe. The problem of the standard model is, okay, that lies in the fact that there is no candidate in the standard model, the good candidate for the dark matter. So that motivates us to go beyond the standard model. Okay. Also, the dark matter properties is still unknown, their identities, and we have the many new physics model proposal, and that propose the many dark matter candidates. And we have at least the many names here. The action that we have the action lecture yesterday, the Francesca's lecture, and the another one, the most popular one, the weakly interacting massive particles, so-called WIMP. Or these days, some people talk about the strongly interacting massive particles, or self-interacting particles, and the feebly, and some blah blah blah. We have the many candidates. Okay, so they're here, and to discuss the dark matter physics and for the lecture today, and I'd like to categorize the dark matter scenario into so-called summer dark matter and non-summer dark matter. The summer dark matter meaning is the dark matter particle has been in a thermal equilibrium with the standard model particle plasma in the other universe. Then at some point, and I will discuss more detail later, and some point in this dark matter decoupled from the summer plasma. This summer plasma is the summer plasma of the standard model. So this is this phenomena is called freeze out. This is one of the main topic of my lecture today. The another category is this is the one category. The next one is of course non-summer dark matter, and obviously, so this dark matter has never been in summer equilibrium. That's the other meaning. Okay. So in a simple scenario, the dark matter particles have been produced by the summer plasma of the standard model. So actually we can consider the variety of the non-summer dark matter scenario, but today I mainly consider the non-summer dark matter, and producing the production of the dark matter in the universe is done by the summer plasma. But the dark matter is not in thermal equilibrium with the standard model particle plasma. So that is so in that case, the production mechanism is called the freeze-in production, the freeze-in dark matter. I put some examples for the summer dark matter and non-summer dark matter. But if you're not familiar with the Suji models, and you can just ignore it. Okay, it's not so important. Okay, So in this lecture, I will review the two popular dark matter scenarios. So that I say, as I mentioned, the freeze in and freeze out scenarios, the corresponding to the thermal dark matter, and this is non-thermal dark matter. Then address some more physics and address some answers to the following questions. Or I'd like to give some clue for your new research in the future, all right, on the dark matter. Okay, the question is what dark matter property distinguishes two scenarios? Well, I already mentioned that the dark matter is actually has been in the thermal equilibrium or not. However, here and I'm going to more details and how to distinguish and this guy is the thermal equilibrium, this guy is not. Okay, and next one is each scenario and how is the observed dark magnetic density produced. Okay, so this is the freeze in and freeze out mechanism, so-called. Then last one, the how to prove the dark matter or dark matter itself, or in the dark matter is the sector, including dark matter. We normally call the sector the dark sector. Okay, and experimentally. So I'd like to address and for this, I'd like to give you some clue, an idea how to do this in this lecture. Okay, and okay, the chapter 2 is section 2 is the basics of the particle cosmology. So I'd like to talk about the very basics. So this is really the basics, and if you know very well, and you can skip it. Okay, so you can take a rest the next 5 minutes. Okay, so the first one is very basic. It's just a unit discussions. Okay. In a particle cosmology, and normally, and just the same as the particle physics, we use the so-called natural unit. And the unit is we set the Planck scale h bar and c to be 1. And also the Boltzmann constant is set to be 1. So doing so, and we can simplify the dimensions. Any dimension for parameter expressed in terms of mass dimension. Okay, the energy is mc squared, the c equal 1, right? So the energy is the same as mass. And the temperature, if you take the Kb set to be the Kb1, and temperature is also the mass. This is also the energy. And the length and the time is the inverse mass. So here I put the example. That's a all straightforward example. And the particle number is has no dimensions, right? So that's a dimensionless quantity. So the mass dimension 0. Okay. And the number density, the number has no dimension, but they divided by volume. The volume, the length cube. Okay, so that means this dimension is mass cubed. Okay, and then energy density, the energy density, the energy divided by volume. So they mass to the mass dimension 4. And the entropy density, the same as the number density. The entropy is just a number, but the density, the denominator, we have the volume. And so this mass dimension 3. Okay. So now the Big Bang cosmology. This is the setup of the dark matter physics. Okay. So this is also the success for the cosmological scenario. So Big Bang cosmology, the basic thing is all our discussion of cosmology based on the Einstein's GR, right? The general relativity. So we consider the Einstein equation. Einstein equation, the beautiful equations. The left-hand side is the corresponding to the geometry or the curvature, right? So this is the Lich tensor, and the G mu nu is the metric, and the scalar curvatures, and then the left-hand side. And the left-hand side is determined by the right-hand side source. The right-hand side is actually the source, and this is the energy momentum tensor. Okay. So the MP is the reduced, so-called reduced Planck mass. And that's a Planck mass divided by square root 8 pi. The actual number is 2.4, well, more precisely 2.44 times 10^18 GeV. So we consider the Einstein equations and with the metric ansatz. And in a Big Bang cosmology or cosmology discussion, we use the so-called Friedmann-Robertson-Walker metric. So this is a very simple metric ansatz based on our observation in a global, very large scale. We know the universe is our universe is very homogeneous and isotropic. So this ansatz, and we can just write down the Robertson-Walker metric in this form, right? So but we need to discuss the evolutionary universe, and this is the time component, that's the line elements, and this is time components, and this is the spatial part. But spatial part is the homogeneous isotropy, but we have the overall factor, that's a scale factor, and that a function of t, that's that represents the evolutionary universe. And then therefore, this is the metric part, and then the right-hand side part, we have the energy momentum tensor. Okay, so the energy momentum tensor in our universe, we have the lots of particles all summarized. Okay, so we have the many particles plasma and the hot and the dense plasma. So hot and dense plasma, the particle and the perfect fluid is a good approximation. So this gets T mu nu expressed in terms of the energy density of the state and the pressure of the particles, and that's a plasma state, and energy density of that and the pressure of that. All right, so this is the setup, and then by using this, and then we can rewrite the write the Einstein equation. We look at the mu nu, the time component, and we have the so-called the Friedmann equation. So this is the definition of a Hubble parameter. Hubble parameter is defined as the A dot over A. Dot means the time derivative of the scale factor. Scale factor is just a function of time. So A dot over A is a Hubble parameter. So Friedmann equation is the Hubble parameter is determined by the energy density of the energy density of the universe, and divided by this is the coupling divided by the Planck scale square. Okay. The another equation, we have one more independent equation. That is the simple form is obtained from the time component and combination of time component to spatial component. And that is nothing but a continuity equation. So energy density, the time derivative, is expressed in terms of the Hubble parameter and the energy density and the pressure of the plasma. All right, so well, I would say the plasma or some matter field there, and anyway, so the source of energy density and obeys this equation. So this is actually it turns out it's actually equivalent to the first law of the thermodynamics. That's just energy conservation. So that means here the S, here the capital S means the total entropy of the universe. And this equation indicates that the total entropy of the universe is actually the variation is zero. So or we take the T derivative of entropy. The entropy is conserved. Total entropy of the universe is conserved, and during the evolution of the universe. So this is the result from the Einstein equation with the Watson-Walker metric ansatz and perfect fluid approximation. Okay, a little bit more, and here I define the equation of state. All right, pressure of the state and the source of the energy density, and expressed in terms of the parameter W times energy density. The normal W. Generally the time dependent, but the simple state like a radiation of matter and the cosmological constant, this is actually time independent quantity. So radiation case is this W is actually 1/3. This is the pressure of the photon is 1/3 of the energy, 1/3 of the energy or density of the photons, right? So, and this is radiation. I said radiation, but generally this is the in particle theory particle physics picture, and any particle which is any particles which are relativistic, and we can apply this equation of state, the W 1/3. So just plug in to the continuity equation. We can easily derive that the radiation energy density is proportional to scale factor power 4, the inverse power 4. So the matter case is the W is 0. That's a non-relativistic. More generally, they will say the non-relativistic particle. So this case is the W, the pressure is just 0. Okay, that's a non-relativistic. So, and that's we can forget about the motion of these particles. In this case, and we can derive that the energy density and of the matter is proportional to 1/a cubed. And another one is the dark energy. And well, recently, so these days we call it the dark energy, but we used to call this the cosmological constant. Not necessary to be the constant, but the well, simplest case, we consider the constant for the W. W is just the constant. We take the -1 is the dark energy definition, actually. So plug this in, and we get the rho dot equals to 0. So that the rho dark energy density is actually the constant over the evolutionary universe. Okay, so this is the typical 3 states. All right, so the knowing this, and this is just a simple calculation, right, from the Einstein equations and the 2 equations, the Friedmann equation and continuity equations. Then now we consider here and the W map and the fitting, and this is the observational result. The 0 or not means and the present the value at the present universe. Okay, at the present. Okay, so I take a ratio of these energy densities are from radiation, basically the photons, right? So this matter is basically the dark matter and the baryons. And this dark energy, or we call, so these days we call dark energy, dark energy. We used to call it a cosmological constant. All right, so this ratio is determined this way by the CMB, the very precise CMB observations. I put this one here. But we know that the evolution of this quantity and the previous slide, right? So then if we go back in time, and we can easily get what's the relation and between them. So at the present, this is a ratio, and the present point is here. And so now we go back in time, and the rho r is proportional to the a to the power -4, and this is the a power -3, and this is a constant. So then the go back in time means and the universe becomes smaller, scale factor becomes smaller and smaller. So if so, and if so, actually at some point the radiation starts dominating. Okay. So if you do some more precise calculations, and actually we see that at this point, the so-called the equal epoch, and the radiation energy density, the matter energy density becomes the same. And this is roughly the temperature of the universe, or CMB temperature of the well, photon temperature of the universe is around 1 electron volt. Okay, so dark matter physics I'm going to discuss more detail today. It happens actually the relevance to these regions, and the temperature is normally much higher than 1 electron volt. And normally 1 GeV scale or 100 GeV scale or even TeV scale. And so the regions and the universe and actually energy density of the universe is dominated by radiation energy density, the photons and the other standard model relativistic particles of the standard model. So temperature is so high, right? So then so here, and we normally consider in the dark matter physics discussions, and the universe, we assume the universe is the radiation dominated area. The universe is in radiation dominated area. Okay, so now a little bit more preparation, the basics, and okay. So, and I commonly discuss the dark matter scenarios, and we consider the creation and annihilation of dark matter particles. Okay, so this occurs, I already stated, in the radiation dominated era. So in which all the standard model particles are in the thermal equilibrium. Okay, so this case is the A, it's the simple calculation where A is proportional to the square root of T. And half is the A dot over A, so the factor 1/2 is not very important in the cosmology. And the order 1 factor is not important in cosmology, actually. And so this case, we can say that the Hubble parameter is just proportional to 1 over T. Okay, the T is the time. Okay. So they're all particles in thermal equilibrium. The temperature is so high, and when we discuss the dark matter physics, and the dark matter can be in the thermal equilibrium or not. Okay, so then I discuss more detail in a minute. But here, for the standard model particles, or generally the particle X, okay, and if this particle is in thermal equilibrium, then we apply the statistical mechanics. So that means the temperature and the mass of this particle is determined. Actually, we know all the thermal properties of these particles, okay, or this particle X. In that case, as usual, the statistical mechanics, and here we use the distribution, thermal distribution function. and 1 over exponential. Well, and plus minus part is for the and the fermions and the bosons, right? And the quantum statistical mechanics. But non-relativistic case that actually this dominates in the plus minus 1 is not so important. The energy is, of course, the Einstein's relations, the momentum square plus mass square. Okay, so now energy number density is an x, and the gx is the degrees of freedom, internal degrees of freedom of this x particle. For example, photon gx is 2, and the Dirac fermion gx is 4, and so on. Okay, and then integrate with respect to the momentum, and then distribution function here. Okay. So this is the general form, and here I put the approximation formula. Again, I forgot I didn't put this prefactor gx and so on. So this is the order 1 quantity. The order 1 quantity is not important for this for my discussion today. If you go to the more detailed if you do the more detailed calculations, and you consider that. So anyway, this case, the temperature is so high, and the much greater than mass, and just consider, and we consider just the mass dimension. Number density mass dimension is 3, and the energy density mass dimension is 3. The pressure mass dimension is also 4. Okay, so in this case, and if the temperature is so high, and the statistical mechanics tells us that this is all controlled by temperature, then then power is from just the dimension simply. Okay, the temperature is the energy dimension or mass dimension, right? But if the particle becomes non-relativistic, and so we have the dramatic change of the number density formulas, and as you know, in that case, in non-relativistic case, we have the Boltzmann suppression factor here. The energy density, of course, the mass of this particle times the number density of these particles, and number density is Boltzmann suppressed. And then non-relativistic means, and the momentum, spatial momentum is almost 0. That means the pressure is 0. Okay. All right, so that's the basics of the cosmology. So now we're going to discuss our thermal and non-thermal dark matter. So corresponding to that, in the mechanism to get the dark matter relative density is the freeze out and the freeze in scenario. Okay. So well, this I just repeat, and we categorize the dark matters into the thermal dark matter and the non-thermal dark matter. Okay. Then now how to judge this particle. So given the particle there, there's some interaction there. In this case, in the how to judge this particle is in thermal equilibrium of the standard with the in a standard model particle plasma or not. How to judge it? Okay, so so this case we consider and the process which change the numbers of the X particle. Okay, so this is actually we are talking about so-called chemical equilibrium. All right. So this case, to simplify the simple scenarios, I consider the dark matter, and here, and let's introduce let me introduce the simple case, the Dirac fermion dark matter. Some new particle there added to a standard model. Okay, exofermion and the dark matter and the Dirac particle. In this case, we have the X particles and X bar anti-dark matter particle annihilation. And introducing this type of interactions, and XX bar annihilating to the standard particle fermions, or standard model particle fermion can create the XX bar particles. That process, suppose we have such process. Then we have this process in particle physics, and we have the cross section, right? We can define a cross section, or interaction manner is known, we can calculate the cross section. Okay, so given cross sections, and we can discuss this particle can be in thermal equilibrium or not. Okay, so let me consider here and the picture for the number of the dark matter pair annihilations. Okay, we have the many X particles, X bar particle, and well, we simply assume that the number X and the X bar particle in the universe is the same, and we don't have any asymmetry. And so for simplicity, in that case, and okay, how many the X particle can annihilate with the X bar, we may consider we may consider the process like this. Okay, and in the rest frame of the X bar particle, one X bar particle. And then X particle beam, we have the X particle beam, and towards the X bar. Okay, and we have the cross section. Then we consider the cylinder like this, and then we have here the cross section. The sigma X bar is the green area. And so this green area or the cross section, the actual meaning is that this is the effective size of X bar in the particle physics or even the classical physics pictures, right? Classical physics pictures. And this is the effective size of X bar. Okay. So this case, and we consider a time interval of big T, okay, the capital T, and all X particles inside the cylinder. And that's a B relative B real is a relative velocity. So I'm talking about the X bar, the rest frame of the X bar. So this relative velocity times T, and it's the height of the cylinders, right? And the cross section times this height is nothing but the volume of the cylinder. So that means here this picture, from this picture, we know in a time interval T, all X particle inside the cylinder can scatter with the target X bar. Okay. So this is the number of, in that case, number of collision or number of annihilation is the number density of the cylinder volume times the number density. It's a collision numbers. Okay. So this case is here simply the nx and the number density of X particle, and the volume is expressed in terms of by the cross section times this height L, right? The v relative velocity times T. Okay. So now we define the so-called annihilation rate. This is just this is the number of collision divided by time interval T. So that's the number of annihilations happening per unit time. So this is just like the X, the number density times the cross section times the relative velocity. Okay. So and then, but here we consider and this process in expanding universe. Expanding universe is universe, and the evolution is determined by the Friedmann equation. That's the Hubble parameter. And that corresponds to the Hubble parameter determines the time scale of the universe. All right. So in the radiation-dominated era, and we are interested so for the dark matter, the relevant to the dark matter physics, and Hubble is determined this way. But in this case, that we know this is proportional to 1 over time. Okay. So that means then we judge. So now here we can judge this particle X is in thermal equilibrium with the standard model particle or not. And we judge that and this way. And this annihilation the rate and over H is greater than 1 or not. This 1 is actually the number of the collisions. Collision is the number of the collisions is greater than 1. Oh, there is a collision, right? Otherwise, there is no collision. So no collision means that this particle is not in thermal equilibrium. Interaction is so weak. All right, so that's the annihilation rate. Is the interaction rate is so small. So that's the meaning. So if you judge this, and you may consider and just use the number of the equilibrium state numbers, like the X particles, then a number density of the X particle in the equilibrium case, and also this is thermal average, the cross section times the relative velocity. So this is a way to judge this particle. We consider X is a dark matter. This dark matter is actually can be in thermal equilibrium with the standard model particle or not. Then we define, so using these formulas, we can judge it. Then if that is in thermal equilibrium, then we say this dark matter is a thermal dark matter. Otherwise, it's a non-thermal dark matter in that category. Okay. Okay, so here to do more discussions, and well, it's always useful and very helpful to consider concrete examples, right? Concrete model. Here, this case that I introduced the so-called Z prime portal fermion dark matter. Okay, I introduced schematically introduced the XX bar annihilation, and that communicated with the standard model fermions, and creating the standard model fermion pair, or standard model fermion pair creates the dark matter pair. All right, so and I put this part, and kind of it depends on the model, but here I introduced a very simple model, something like the QED like and the QED like scenario. Okay, I introduced the dark matter. Well, I just see sorry, I changed the notation slightly. And this is the dark matters and the anti-dark matters, and then they are coupled to the standard model fermion mediated by the so-called Z prime. Z prime is the charge neutral photon-like particle, but it is massive. Okay, so in the later we introduced this Z prime, some class of some simple models of the extension of the standard models, and the Z prime is a new gauge boson. So far, you think we think this is like just a vector boson. Okay, so these are coupled to the fermions, and with a coupling, the dark matter pair with a coupling G chi, and the coupling with a pair of the standard model fermion. This is the coupling GF. For simplicity and calculation, for calculations, I said the Z prime mass. This mass is much lower and much smaller than dark matter mass. Okay, but just yes, just a way to simplify the calculation. Right. All right. So then now we consider this guy the thermal equilibrium or not. Okay. The first we calculated cross section, and the simple calculation of cross sections is this is the Poisson factor is not really precise. And see the Feynman diagram, then we can get the rough formula like this, right? So this is the first the cross section has a mass dimension -2. So there we have the mass dimension in the denominator. This is the Mandelstam's S, and the 4 pi is the usual the phase factors. 1/4 pi is the phase factor roughly, and then we have the coupling squared, right? So that's a rough formula. So yeah, the more precise calculations we might have the factor 4, factor 2, and so on, but it is not very important in a cosmology discussion. So now in this case, once we get the cross-section formula here, and we actually apply our way to judge this guy is in thermal equilibrium or not. Okay, and we compare the dark matter annihilation rate, and this is the number density times the cross sections. Okay, but sometimes I put the bracket for the thermal average, but this case roughly we think this one is this one is the same as this. Okay, so this case we just consider the dimensions here, some temperature T, and this is the dimension 3, so the T cubed, right? So this is the dimension mass dimension -2, denominator high temperatures, and everything determined by temperature, so that the S is replaced to the temperature square, so that you can easily get this form. All right. So the expansion rate of the universe is the Hubble, but the energy density divided by Planck squared and square root of that. Energy density is the mass dimension 4 quantity, and that's a high temperature, so they're all controlled by the radiation. That's the energy density is just a T to the power 4, right? So then square root, and we get the Hubble is roughly the T squared when Planck. Right? Just considering the dimensions, we can easily get all the equations. These equations right up to some order 1 factors. All right. So now we compare this and this, and so if this quantity dark matter annihilation rate is greater than Hubble, and we say this guy is a thermal dark matter. Otherwise, non-thermal. So these simple scenarios, and just you apply this one, and we can see that okay. So G chi times GF, this coupling product is greater than square root of the mass ratio, the mass and the Planck mass ratio, and this thermal dark matter. Otherwise, and cannot get in thermal equilibrium. Okay, so this is the way to judge this guy is a dark matter. This dark matter is a thermal or non-thermal. Okay, so next, and so now the judge or this guy is the thermal or non-thermal. Then the next step is how to evaluate the dark matter electric density. Okay, so we have the observation of the dark matter electric density. So now for we'll study the thermal dark matter scenario, and we evaluate the dark matter electric density by solving the Boltzmann equation. Okay, so yeah, so this is so-called Boltzmann equation. I give you the idea that how to get the Boltzmann equation. That's the physics meaning is really simple actually. Okay, suppose the n particles and x particles and x bar particle number are the same. Suppose, so we don't have any asymmetry like baryons, and so this case in the number density and number of the x is determined by time variation. Is determined by determined by the creation and the part and the annihilation part. Yeah. So annihilation part is nothing but the annihilation rate times the number of X particles, right? So, and this annihilation part is just by using the previous formula for the annihilation rate and times the X particles or number of the X particle. It's the change of the X particle numbers. Okay, and the creation part is I just leave this one. The just creation, all right? So from this formula, we can say the left-hand side. Let me calculate the left-hand side. And the Boltzmann equation expressions, and normally we use the instead of the total number of the X particle, instead of this, and we use the number density of the X particles. Of course, the total number of the X particles is the number density by definition. The number density of the X particle times the universe volume. Then apply the time derivative, the number density of the X derivative times volume and the volume derivative. Right? So B, we push the B out, and we have the form like this. But the universe, the expanding universe, and we have the very simple formula for this. Okay, so you see, and the volume is of course the proportional to the scale factor cube, right? So then this quantity is nothing but actually the Hubble. And then the derivative, the cube, this we have spatial dimension, number of the spatial dimension is 3. So then we have the factor 3 out, right? So, and this quantity is expressed in this way in terms of the Hubble and the number density. And then we already evaluated this part, right? So the annihilation rate times the number of X part is this is the annihilation calculations, and then number of the total number of the X particles is the number density times volume, of course. So then this case we just write this way, right? Then and this quantity and the last term in the right hand side determined this way. So now we use the balance. Okay, if the X particle is in thermal equilibrium and the X particle is in thermal equilibrium, that means the creation number, the X particles, and annihilation number of the X particles must be the same, right? And that's equilibrium means the no change. So that means, and if you take this quantity to be the equilibrium value, and the equilibrium values, the right-hand side must be 0. So that means this creation part and the creation part is nothing but this quantity by replacing the whole quantity in equilibrium value. Okay, so this is the formula in that way. Okay, so now and rewrite the whole stuff, and we get the normal the Boltzmann equation. So the Boltzmann equation on the hand side is the number density derivative plus the 3h and x. So this part is from the dilutions of the universe. Okay, if the universe is not expanding, the h is just 0. So that this is just the nx derivative with respect to t. Then the right hand side is the annihilation cross section part, and then the x squared and minus equilibrium case x squared. Right. So this part is a creation part. This part is annihilation part. Okay. Then of course, and see the x, the value, it's the same as the equilibrium value, and the right hand side must be 0. Even so, you can see the universe. If the universe is expanding, of course, and x is diluting, right? So, okay. So yeah, this is the original Boltzmann equation, and normally in solving the Boltzmann equation and for the dark matter physics, and we normally use the so-called new quantity, so-called yield. And this definition is the number density. I just dropped the x and generally the number density divided by entropy density. So this quantity is very useful because the multiplied by b for the numerator and the denominator and the numerator. So the NB is nothing but the total x value, so total number of x particle. And then denominator is the total entropy. But we already discussed that the total entropy from the Einstein equation, the total entropy is conserved. This is just a constant during the evolution of the universe. So that means the yield is has the very clear physics meaning. That is actually the total number of x particle in the universe, whole universe, normalized by whole universe entropies. But this is constant. Okay. All right, so using this, the Boltzmann equation, we rewrite the Boltzmann equation of this form. We use, and normally we replace the Boltzmann equation by using this quantity, dimensionless quantity. Originally, the time derivative, but we make the time corresponds to the Hubble. Hubble determines the energy density of the universe. But the energy density of the universe determined by temperature, right? So that's the time. We have the one-to-one correspondence between the time and the temperature. And here, and the dark matter mass is fixed to be some numbers, and we introduce the X quantity, which is the dimensionless, all right? Okay, so in this way, and we can solve the Boltzmann equation. All right. Well, nowadays we can use the many softwares and the Maple and mathematicals, and we can solve the Boltzmann equation, or so C-chord or Fortran's all days. All right. So this case in the thermal equilibrium dark matter case, and the initial condition is, of course, they are in the thermal equilibrium. So the initial condition is the very small, the very high temperature, high temperatures, and the yield value must be the same as the equilibrium value. Okay. Equilibrium value of the yields is determined by just the temperature and the mass of this particle. So this is the plot for the equilibrium value. This is completely determined by the statistical mechanics if this particle is in thermal equilibrium. Okay. However, solving the Boltzmann equation, we can see the very interesting behavior of the solution. And so this is actually initially the y is the same as the y cube, but the tracing the tracing the equilibrium value. But at some point, it's because of the effect. This is due to the effect of the expansion of the universe. And at some point, this particle and the decouple from thermal plasma. This is so-called freeze out. Okay. After that, we see that quickly goes to the constant. You see then record that's the y, what's the physics meaning of y. Physics meaning of y is just normalize the entropy, total entropy, constant normalize the total number of this particle in the universe. So that becomes constant means, and we don't have any creation, we don't have any annihilation of the dark matter after the decoupling. Okay, we call it this nature property decoupling, or we call it the freeze out. After the freeze out, we don't have no change. We have no change of the dark matter, total number of the dark matter in the universe. This is the decoupling, so-called decoupling, or freeze out scenario. Okay. The previous scenarios, and we have the cross-section formula. In this case, here I draw this plot is for the parameter set to be these numbers. Actually, in this case, we can reproduce the observed dark matter electric density. Okay, so observed dark matter electric density is the density parameter. That's the dark matter density divided by critical density, and normalize the Hubble parameter here, and express in terms of this. And the S0 is S0 is the present universe entropies. And the Y is the number density of dark matter divided by entropies, right? So the S canceled out. So the numerator is nothing but the mass of dark matter times number density, which is the energy density of the dark matter, right? So these are mainly from the entropy of the photon, and then the critical density is measured, determined by the Hubble parameters and the Hubble constant, the Hubble parameter at the present, Hubble constant. Okay. So then the CMB observations tells us that omega is squared is around 0.12 very precisely. Okay. All right. So this case, actually, this value is reproduced by the 1 TeV and gets the coupling to be the 0.1. So this is just that's just we choose the suitable value for the parameters. We can reproduce this. Okay. Before moving to the freeze-in scenarios, I'd like to mention the so-called WIMP dark matter miracle or WIMP miracle. So we have if you look at the WIMP scenario or thermal dark matter scenario, then solving the dark matter, solving the Boltzmann equation, actually we can see the very interesting result. Okay. So the weakly interacting massive particle is a primary candidate for the thermal dark matter in our universe, and many new physics models include the WIMP. Okay. And with the given annihilation cross sections, we can solve the Boltzmann equation. So the equation is simple. Actually, the given the cross section values that we can easily solve it. And to get the observed dark matter density around the 0.12 more precisely, and actually we can see that the cross section and the input cross section inputs to solve the Boltzmann equation it turns out to be around 1 picobar. Okay. So then we consider that the observation, the dark matter density, observe the dark matter density, and for the WIMP scenarios, we know what's the suitable cross section to get this value. So actually, that's the 1 picobar. So we may parameterize the cross section that something like the photon mediated like process, and this is the very much non-relativistic particles, and so we have the well, just because of the dimensional analysis and the cross section in the mass dimension -2, and they're characterized by dark matter mass squared in the denominators, right? So then we may express the form just to parameterize this way, assuming that the interaction is kind of similar to a QED interaction. If you introduce the QED, the known values for the fine structure constant, you can find this to get the 1 picobar, and you will find the dark matter mass is around the denominator scale is around the 500 GeV. Right, the changing the couplings a little bit, and you can vary the mass scale of the dark matter or physics dark matter physics scale. It's around 100 GeV to the 1 TeV. Very interestingly, and the dark matter physics observed in the WIMP if the dark matter is a WIMP or thermal dark matter, and observe the dark matter density, and indicates that suggesting us that the dark matter physics scale is around 1 TeV, 100 TeV to the 1 TeV. So this is so-called the WIMP miracle. And the kind of miracle, why the scale is the scale we know, or the scale for the LHC, okay, for the LHC experiment. Okay, so now we consider another category, that's the non-thermal dark matter, so the non-thermal dark matter case. And the Boltzmann equation is actually very general, and even for the non-thermal dark matter case, and we can use exactly the same form. And then, but this case, and the difference is just the initial condition is different. Non-thermal dark matter means, and we don't have the dark matter is not thermal equilibrium. That means the dark matter density is we expect and much smaller than the equilibrium value. Okay, let's say the set here, this one is very, very small, just a 0, very, very early universe. In that case, in that case, the difference of in the technical point of view and solving the Boltzmann equation, the difference of the thermal dark matter and the non-thermal dark matter and the dark matter density calculation, the difference is just the initial condition difference. Okay. All right, so this case, the Boltzmann equation, the same form, but here the non-thermal dark matter case, and this is not in thermal equilibrium. We assume that the initial value of the dark matter is just 0. The dark matter density is just 0. Then solve the Boltzmann equation. The previous the Z prime Porter simple scenario, Z prime Porter dark matter scenarios are actually the cross section is expressed in terms of the x squared, the proportion to the x squared. If you plug in the cross section formula here, you can simply see that the freeze-in case and freeze-in case, this part is independent by x actually. And also the freeze-in case and the initial value is 0, right? Very small. So that means in the right-hand side and this part dominates. And so we can forget about this term. So in that case, the freeze-in case, actually we can easily solve the Boltzmann equation. So if you do so, and here, this is our Z prime Porter example, and we see the left-hand side and the right-hand side become there. So we find the right-hand side is just a constant. Okay, I show you the numerical result for the set by setting the dark matter mass to be the 1 TeV and coupling to be these numbers. Actually, this number is a suitable number to reproduce omega h squared observed value. Okay, and so that this is a solution. And the freeze-in case and freeze-out case are quite different. The freeze-in case is initially the equilibrium. Then there's some point tracing the equilibrium value. Then some point the decouple becomes constant, right? Well, the freeze-in case, initially we have no dark matter population, so that the y becomes very, very small. It's starting from the very, very small value. But solving this one, we have the creation of dark matter from the thermal plasma. Interaction is so weak because why this dark matter cannot be in thermal equilibrium. Even so, the thermal plasma, this is quantum mechanics, and the thermal plasma, some probability can produce the dark matters. So then the time goes by, the dark matter, we have the more population of dark matters, but the dark matter production stops at some point. This point is actually nothing but the temperature is the same as the dark matter mass. This is just simply the kinematics. Okay, so dark matter, the temperature is roughly the average momentum of the standard model particle. This momentum is smaller than dark matter mass, and becomes smaller than dark matter mass, and kinematically, and the standard model thermal plasma cannot produce the dark matter. Then the production stops. Okay, so that's the reason why the y becomes constant. After that, again, the freeze-in mechanism case, and y becomes constant. Okay. All right, so these parameters, and we get this one. So you compare this case, the freeze out case. The freeze out case is they are in thermal equilibrium. That means the interaction is much stronger than this case, right? And the previous case, you can, if you look back the numbers and the G chi GF in the thermal freeze out case scenario, it is this is I took the 1.1, but if freeze in case, and this is a really small value, 10⁻⁶. Okay. So, but both cases actually the omega h squared 0.12 is reproduced, right? So, but the scenario is completely different, right? Okay. Yeah. So 3 minutes. Yeah. So I have no more slides, but okay. So let's just quickly discuss this part. So the last topic is the experimental probe of the dark matter or dark matter related sectors. But here I consider the freeze-in, freeze-out, the Dirac fermion dark matter scenarios. And also I want to mention that the lifetime frontier experiments these days people are working for. Okay, so okay, let's consider the Z prime polar dark matter scenarios. And suppose the coupling is very small, suppose. In this case, the Z prime and the new particle, and of course can decay. This is massive, they can decay into the standard model particles. In this case, the standard model fermion pair. However, the coupling is really small. This particle lifetime becomes longer. So this Z prime can be long-lived. Okay. Actually, recently we have the many proposal and planned experiments to search for such long-lived particle, long-lived the electrically neutral particle. Okay. So the one example, the simple new physics model example is the so-called B-L model. That's a baryon number minus lepton number model. So this is kind of technical, the technical thing. And so I can skip. This is the very good models, and the G prime portal, G prime is there. Okay, so G prime is nothing but the new gauge boson related to the baryon number minus lepton number gauge interaction, just like the photon light. And the charge of the particle, the standard model particle determined by the baryon number minus lepton number. Quark has a baryon number 1/3, lepton number 0, so the charge is 1/1000. So interesting of this model is that actually, and theoretically, if you introduce the new gauge interaction, we have to consider the anomaly free condition. So this case, to make the theory anomaly free, we have to introduce the right-handed neutrino here. So now seen discussed the neutrino mass generation in the discussion sessions, and then I've seen the Professor Cha discussed the neutrino mass generations, right? So, and this is actually the right-handed neutrino, and we discussed the couple days we discussed it yesterday, and the Monday and Tuesday, and then this is the particle this is the particle is important for the mass generation of neutrino mass generation. Okay, so my time is I have a couple of minutes then. Okay, so yeah, so just to skip
we started 5 minutes late, so I think you can definitely use 5 minutes.
Oh yeah, thank you very much. Okay, I use this 5 minutes. Okay, 5 minutes. Okay, so these properties, I just listed a property of this gauge to B-L extended models. And so I just skip the detail, but the gauge in the B minus L, actually standard model has the global B minus L symmetry. This is just a gauged version of the local version. Okay. If you have the global symmetry, we can make it local. But once we make it local, the gauge symmetry, and we have to consider the quantum anomaly and the chiral anomaly. So this case, we need to add the right-hand neutrino. This right-hand neutrino is just nothing but the particle we need to generate a neutrino mass. This is so-called the seesaw mechanism. And if the right-hand neutrino mass is big, and we have this effective operator, and like the HHLL, if the standard model, the Higgs doublet, H the Higgs standard model Higgs doublet, it develops the vacuum expectation value. Actually, we can get the standard model neutrino mass of the form like this. Interesting thing here is that this is from just like the same as the quark mass or the charged lepton mass way, and just pick up the Higgs vacuum expectation value through the Yukawa interaction. However, we have some big mass scale in the denominator. Sorry. So we have this scale. If we have the numerator, denominator, and the hierarchies, actually we have the big suppression here. So this is so-called seesaw mechanism. That's the reason, interesting explanation why the neutrino is so light. Okay, neutrino mass is so small. Right. Okay, so I talk about the
M right, the scale M right. How big is this scale?
I'm sorry?
The scale M right. M
yeah. Oh, scale M right is you can, well, here I just take the M right is we can take the variety of M right scale, and just here I take the hierarchy. And so then actual value determined by your choice, and to reproduce the neutrino mass value in oscillation data. Well, this case I consider the 1 TeV scale. Okay. So so Z prime, this is Z prime portal, Z prime scenario. Actually, we have the so-called phasor experiment that is recently approved experiment, and that new experiment sun to search for the long-lived exotic charge neutral particles. And the experimental site is actually the away from the 400-meter away, and down the atlas, the detector interaction point. This is the beam line, the proton-proton collision LHC beam line. And some collision happens, and some particles, many hadrons created for the forward direction. And some of them may decay to the long-lived electric charge neutral particles. So this particle created that propagates to this point, and this particle is very long-lived. After the 480-meter propagation, that particle can decay. Then the idea is to detect such the particle decay. All right. Okay, I can skip this one. So they already studied a variety of the new physics model, which includes the long-lived charge neutral particle. And then B minus M, I introduced a B minus model. B minus model Z prime is also studied. Okay, this is a list of the studies, and they call the dark vectors, dark scalars, dark. That means they are the charge neutral. Okay, so and long-lived particle. Okay, so this is from their analysis, and for the Z prime boson and in the B minus model. Okay, the new gauge boson. If the new gauge boson mass is below the 1 GeV or so, and the gauge coupling is very small, and they are the Z prime long-lived. So this case in the phasor experiment can detect the region like this. This is a phasor experiment, and we at the LHC round 3, and the high luminosity LHC the upgrade, and they extend the such region by the phasor 2. Such region is like this. The shaded region is actually already excluded. Okay. Okay. So yeah, I have the 1 minute or so, 1 minute or so, and I just quickly discuss that one. So, and the B minus model is a good model for the seesaw, but actually the dark matter is still missing. That it is quite easy to add and the dark matter candidate to this model. This is just the Dirac fermion dark matter. So this is just the model we discussed before. Okay. So I said the kind of simple toy model, but this model is actually the very nice model and the very simple extension of the B minus model. So we introduced the dark matter, the Dirac fermion dark matter with some B minus charge Q. Okay. So in this way, we already discussed the dark matter pair couples to they communicate with the standard model particles, right? So then they are two. Then we already calculate the theoretical density of the dark matters, right? So the freeze-in case scenario, okay, a freeze-in case, they're setting the dark matter mass, and we have we can just change the charge values, and we can actually show that which region is the satisfy the dark matter radical density values. Okay, along this line, the omega h square 0.12 reproduce in this model. And so you can see that the overlapping with the phasor search reach and so on. Okay, okay, so I skipped that one. So we can do the same thing. That this is our recent paper with the sum of organizers and the Kaiser Shafi and the Dijesh and me and Newton Nash and my wife Satomi. And so this case here, we consider the same model, but the dark matter mass is smaller than the prime case. So we can plot the result like this. The point is the detail. Just skip the detail, and the point is, the lifetime frontier experiment can search for this long-lived Z prime particle, Z prime, and in the B minus model, and the Z prime model in the future. Okay, so this is the dark matter freeze-in case scenario. Both the freeze-out, freeze-in case scenario, we can search this Z prime dark matter. Z prime, so not the dark matter, Z prime, long-lived Z prime particles. Okay, all right. So okay, that finished, and okay, all right. So this is the conclusion or summary, and the existence of dark matter required us to extend the standard model for incorporating the dark matter candidate. And the many dark matter scenarios, and consider here and the thermal and the non-thermal, and the freeze-in, freeze-out mechanisms to get the right abundance. Okay, and this case we have the simple scenario like a Z prime portal dark matter. If the Z prime portal, the Z prime couples to the standard model particle very weakly, and this Z prime can be long-lived. And actually, we have the many planned experiments to search for such particles. This is a really exciting scenario for future, and related to dark matter physics. Okay, so that's all. Thank you very much.
Okay, thank you very much, Nobuchika, for this really interesting talk.
Thank you.
And without wasting any time, let's go straight into the questions. We have several. So I'll read them off in the order that they appear in the chat. But if you are able to unmute and ask the question that you typed yourself, you're welcome to do so. So the first question I see is from Rishikesh. Are you around and able to unmute? I'll ask the question. So the first question, he has two questions. The first one is, when you talked about entropy conservation, I guess the question is, do you mean energy and not entropy? Doesn't the total entropy always increase?
Total entropy. Yeah, here so far the total entropy of the entire universe is just constant. We can increase the entropies away. Some particle decays and creates the entropy. But if such thing happens and such thing doesn't happen, and total entropy of the universe conserves. So that is the second equation from the Einstein equation.
Right. The next question is from Thong Nguyen. If you're there and can speak, you can ask your question. Yes.
Thank you. So I have several questions, but the first one is, can you explain the GX term, which I think is the number degree of freedom in slide 16, and how to calculate it?
Oh, 16. Okay, let's see. Yeah. For this one, for example.
Yes.
Oh,
yeah,
well, this part is actually easy. Well, you can neglect the mass term, right? Because the temperature is so high.
No, I think he was just asking about the GX in front.
Oh, sorry, GX.
The number density, right?
Sorry, GX. This is just the degrees of freedom of the particle. For example, the photon case, and the photon has two polarizations. Right. So in that case is just you count two. This is just internal degrees of freedom of the particle. For example, the Dirac fermion you have the Dirac fermion, we have the particles, spin 1/2 particles, and they are spin 1/2 antiparticles. So we count, and we count spin 1/2 and the plus 1/2 and the minus 1/2, right? So the particles and 1/2, 1/2, and minus plus minus 1/2, the antiparticle plus minus 1/2, then you count 4 in total.
Mm.
And the
So,
scalar
but in the radiation, sorry,
Yeah.
but in the radiation era, that maybe if we count the W and the Z, they also massless, and they also just have 2 polarization, not 3. Like
yeah, it's okay. It's okay. Yeah, you can consider that. And the temperature is so high, and you can consider, you can count that way. All right, but you can count. This is the Higgs mechanism, and the number of degrees is the same, right? And so, and then we'll just see at the count. The temperature is so high that you can count the W and Z that are massless, and then add the Higgs and the degrees of freedom. Higgs is a doublet, the complex doublet, right? So, and the Higgs has 4 degrees of freedom.
Yeah, thank you. I also have several questions, but maybe let the other participant ask the question first.
Sure. If you have some time, we can come back to your questions. So there's also a second question by Rishikesh again, which is, I think this was in the context of when you started talking about freeze-in and what the reheat temperature is. So his question was, wouldn't the reheat temperature here simply be the temperature corresponding to the mass of the Z prime boson? If it is less than this temperature, then dark matter will always remain in its equilibrium density, right?
Actually, the freezing temperature, the reheating temperature, here I consider the reheating temperature is much, much higher than the dark matter mass. And this is the reheating temperature from after inflation. I didn't talk about the inflation scenario, and the standard paradigm of the modern cosmology is the inflation takes place before the Big Bang, and so after the inflation and inflaton that causes the inflation and the decays to create the standard model particle. Then they thermalize the universe. So that's the heating temperature. And I said that here I consider the heating temperature much, much higher than the dark matter mass.
Yeah, so I think if I can reword his question, I think what he means to ask is, in the Z prime model, if the reheat temperature is heavier than the mass of the Z prime, is dark matter in equilibrium in that scenario, or can you still get freeze-in also in that?
Freeze-in case, freeze-out case, and that's determined by the coupling. So that the reheating temperature is so high, and the freeze-in scenario, still the dark matter is not in thermal equilibrium. Freeze-out scenarios and dark matter is in the thermal equilibrium.
Right. So this is not controlled just by whether the reheat temperature is bigger or smaller than the mass of the Z prime, but also by the couplings involved.
Yeah. So normally that we take the reheating temperature much greater than the dark matter mass and any other masses, the mass of the particle.
Right. So then
okay.
So he says thank you. So I think we answered his question. So the next question is from Himal Oli. Himal, if you're there, you can unmute and ask your question. So his question is, can you explain the terms hot relics and cold relics? And also there's a second part of the question, which is, can you explain the terms freeze in and freeze out and how they're related to couplings?
I see. Well, the hot and the cold depends on the kinetic energies. And so, you can simply, of course, it depends on which point of the history of the universe, and that guy is a hot and a cold. But normally we consider the hot and the cold, the separation of hot relic and the cold relic, and especially for the dark matters. And that is the structure formation error. The guy is the still relativistic or non-relativistic. So that's actually a way to distinguish the hot relic and the cold relic. And freeze in, freeze out case, and say the freeze out case and the interaction manner. Here I consider the freeze out mechanism, and the freeze out happens in this point. Let's say simple scenarios, and here this point, right? You can see that this point and x is greater than around the 20. So this is greater than 1. So x is greater than 1 means, and the temperature is lower than the mass of the dark matter. So here the kinetic energy is the much smaller than mass, the mass of the dark matter. So this is non-relativistic. This case we call this dark matter the cold-relic. Yeah. So and freeze-in case depends, but actually here then the freeze-in case is also still here the cold. And so here the production of this particle, it's a very early universe, and the temperature so high, and the produced dark matter will be the momentum is the same as the momentum of the produced dark matter is the same as the temperature order. But this is produced in this way. The finally and the production stops, and this point is nothing but the temperature, the mass. But after that, the expansion of the universe, according to the expansion of the universe, these particles and the redshifted. So the kinetic energy becomes smaller and smaller. So, and well, this case, well, they simply, this is also the cold relic actually.
Great. So the next question is from Saurabh Niyogi. Saurabh, if you're there, you can unmute.
Yeah, hi.
Yeah.
So my question is, you used dimension analysis for mostly for the high temperature case, but does that hold for low temperature case as well?
Low temperature case is just the well, roughly okay, low temperature, but actually you have the some funny formula here, right? So yeah, so the dimension part is not working very well actually.
Right.
So right, yeah. But maybe but this case in the temperature dependence is actually power is maybe not so important. You may think just focus on the Boltzmann factor separation here. Exponential separation is more important than this one. So
okay, yeah, right.
So
and
but of course this part is you need to carefully calculate, of course. Yeah.
Okay. Yeah, and I have one more question regarding the Z prime example scenario that you showed. So you have a relation like G chi times GF is greater than or equals to M dark matter by M Planck, right? For whether it is a thermal or a non-thermal case.
Yeah.
Right. Yes. And when you show for the thermal case, G chi and GF, you took the value 1.1, which gives the correct omega E square, right? For the correct relic.
Right. Yeah.
And for the non-thermal case, your G chi, GF are both very small, 10 to the power minus 6
right.
order.
Yes, that's right. Yes.
So is it accidentally occurs that that this formula holds for thermal and it satisfies the right relic?
I see. Okay, so you can think this way. For example, this case is a freeze-in scenario. Okay?
Right.
We know that the coupling is really small, right?
Right.
And then if you increase the coupling, you can produce more dark matters. So in that case,
exactly.
So this line they're pushing up.
So the line goes up, right?
Yeah, goes up. Then if the line actually and have the intersection around here, for example.
Right.
After that, and this guy becomes the summer dark matters, right?
Okay. Yeah.
So this case, you can forget about the freeze-in dark matter scenario. Some point in our universe, and even starting from the zero population of dark matter, but the coupling is strong enough, and that's actually becomes equilibrium quickly normally. So then that becomes the freeze-out dark matter.
Okay. And this particular the formula, I mean, which is obviously a tentative one, like G chi times GF, the product of couplings is greater than or equals to M dark matter by M Planck. So that holds only for this kind of particular model, right? When you have this kind of diagrams.
Yeah, that's right. Yes, this is the whole. Yeah. If you change the model, then you just evaluate the gamma and the H formula, and then you see in which case which parameters. And the freeze in, which parameter freeze out. Yeah.
Right. Okay. Thank you.
So next we have Ashok Rai. Ashok, are you there?
Can you, Nabushika, can you extend this model to embed it in some body sum or some left-right symmetry? Because U1 is minus L is natural.
Yeah. Dark matter part is difficult. Yeah.
Is
Well,
it
Dirac case, yeah. Well, because of the Dirac case, and we set here the charge Q some arbitrary charge. So, and then the question is the how to unify the dark matter with other particle, known particle. Yeah. So yeah, of course, and the partner is also the new particle. It is okay. Yes, it is okay.
Yeah.
Yeah. It is possible. Yes.
Okay. Thanks.
Right. So Ashok, you there? So Ashok asked, is there any relation between dark matter and plasma? If yes, then how? I suspect he had some specific idea of what the plasma is, and that's why I was trying to ask him if he could elaborate on that question. But this was the question: is there any relationship between dark matter and the plasma?
Oh, probably the plasma means the standard model plasma, or relation means
Maybe he means the thermoplasma.
yeah, thermal plasma case in the dark matter, in the thermal dark matter case, and the dark matter is also the part of the plasma. They are in some dark matter is in thermal equilibrium with the standard model particle plasma. And yeah, freeze out case and freeze in case, and dark matter never gets in the thermal equilibrium. So that means, and the plasma particle just release the dark matter in some probability, with some probability. Yeah. Or we can consider the temperature of the dark matter and the thermal plasma, and the temperature is determined. And then the dark matter is in thermal. Dark matter is the thermal dark matter, and that's in thermal equilibrium. The temperature of the dark matter is the same as the thermal plasma. But freeze out case, and this guy never gets in the thermal equilibrium, and we cannot. We don't have the well, in some sense we can define the temperature, but we don't need to set the we don't need to define the temperature for the dark matter.
Yeah. So Dong, I remember you said you had more questions. Maybe we have time for one very quick one, but then we have to move on to the next.
Okay, actually I have two, but yes. So
pick one.
Yeah. So can you explain I see that the term S-wave approximation and P-wave approximation a lot in dark matter cross-section annihilation calculation. So can you briefly explain how to calculate the S-wave and the P-wave approximation?
Oh, the calculate. Oh, I see. Somehow. Well, actually, the S-wave and the P-wave, you can actually just the velocity expansion, right? You can do.
So you show some you show one equation for the cross section. That's either S-wave, right? Because that's
See, mostly here I consider the S-wave, but that's the reason why I just set the toy models in the Dirac dark matter. But if you make it a Majorana, then you have to consider the P-wave actually. So in the P-wave case, you have the velocity suppression actually. So the cross section becomes smaller. But of course, and brute force way or the more precise way, and you just get the cross section formula as a function of the S, okay, Mandelstam S, right, or T and U, and so then plug this in. Then using this one, you can take the thermal average. Yeah. But actually, the thermal average, the cross-section formula is a simple formula that actually we have the good approximation for the thermal average formulas actually.
Okay, thank you very much.
Okay, with that, I think now we have to thank Nobuchika for answering all the questions as well, and move on to our next speaker. So thank you again.
Yeah, thank you.
And our next lecture will be by Professor Seema Sharma. We can see you now. You might be, and we can hear you also. So Professor Seema Sharma is from Pune, from the Indian Institute of Science, Education and Research, and she will give us an experimental perspective on various standard model and BSM scenarios. So Seema, if you could share your screen.
Yeah. So
Perfect. We can see it in full screen. So yeah,
perfect.
you can start whenever you'd like. Thank you.
Okay, so thank you very much to get me started. And Professor Okada has given us a tough task to create these particles and discover them also. Now, giving an experimental perspective here becomes a very broad topic. So I have tried to give the salient features of the program and really not like focusing only on one topic, but then you will see that, okay, I'm focusing on one topic in several like subsections. But if there is any interest, I will be happy to come back and discuss with any of you if you want to know more. Because the experimental part cannot start without like first discussing what our tools are, and that itself takes like part of the time of the talk. So let's get started. Let's try to see where we stand. So the general outline of my talk is like, I will just talk about how we go about studying the fundamental particles predicted by the standard model and beyond. And those we already know, already have seen, and those we expect to see. And how do we go about studying these fundamental particles? Now here I will try to like discuss a few general aspects of the standard model and Higgs measurements, which Professor Noshin has also talked about, and also the BSM searches at the CMS experiment. But the same are also mirrored by the ATLAS experiment. So we have some sort of a complementarity. And also it's a personal selection of the topics, but the full information is available from the CMS and ATLAS, the publications pages. So now start with, people can still hear me, right?
Yes.
Yeah, perfect. I do have some internet glitch time to time, so let me know if you can't hear, or in between, just let me know that I'm still connected.
Sure.
Thank you. So we have already discussed about the standard model of particles, and basically this is the summary here. We have the 3 generations of the electrons and quarks, and they are identical in every aspect except their masses. And then the way we understand their interactions so far are that the interactions are mediated by the gauge bosons, which are spin-1 particles. For the electromagnetic force, we have the photons, the strong forces mediated by the gluons, the weak forces by the WNZ particles, WNZ bosons, because these are all spin-1 particles here. The gravity is not yet reconciled in this framework. And how do we understand that these particles get their masses? Because each generation is heavier than the previous one, the particles. So far our understanding is that it's a fundamental scalar boson in the theory, which is sort of Higgs boson. And the way all these things, what I call the traffic rules, that how these particles interact with each other is given by just this mathematical formula. Basically the mathematical formulation, which is what we call the standard model Lagrangian. Now, I think this part is sort of a revision for you, because this is also discussed earlier in the previous lectures. The standard model has been successfully tested at the various collider and non-collider experiments with very high precision. Until the beginning of the LHC, the Higgs boson was missing, but in 2012, we have also announced the discovery of the Higgs boson. And since then, for the last 1 decade, we have been really looking into the details of the various properties of the Higgs. Now, just to be sure that all of us are on the same page, this figure here is essentially referring to that the black dots are the data. I'm just trying to see that, okay, how to read this plot, because I'm not very sure of all these students what level of training they are from. So just a quick note here is that the solid colored ones here are the ones which we are expecting from the standard model. So the x-axis tells we are talking about the Higgs going to ZZ, and each Z boson decays to 2 leptons. So basically we have either 4 muons, 4 electrons, or 2 muons and 2 electrons. So we are looking at the invariant mass of these 4 particles. And what is being shown in the solid, the blue color or the green color, is what we expect from the standard model processes. But when we looked into the data, we found something that was not explained by what we already knew. And this is essentially what gave us that, okay, there is something new going on, and that one came out to be what we were looking for, the Higgs boson. Okay, so that's what we again said, that the standard model is a remarkable, successful theory. And moving ahead, so what do I mean by that? The standard model has been successfully tested at various colliders and non-collider experiments with high precision. Basic general idea is that the standard model, we know which particles interact with which other particles. Here you can see, for example, gluons doesn't talk to any other leptons or anything. It just talks to the particles which carry the strong color, that is the quarks. Similarly, like the neutrinos, they are just the weakly interacting neutral particles, so they don't have any strong or electromagnetic interaction. They only talk via the weak interactions, and so on. So using this knowledge, we can try to figure out, like, we go and do our experiments, try to measure the properties of these various vector bosons, their interactions among each other, their production rates, a variety of such, and all the standard model parameters also, and try to see where we stand with the theoretical predictions. And all these things are like picked up from one of the global fit papers, where we try to put in all the inputs from the experiments we know and try to predict these parameters from the theory also and compare with the measurements. And many of these are really sort of coming out with the per mil precision. That is, the precision is of the order of 1 per million kind of, right? So that's what we say, that, okay, these have been successfully validated against the data at very high precision. A similar example is just here, just to show you that this is in the plane of the W mass and the top mass, which are highly sort of constrained. I mean, if you put together the Higgs mass, W mass, and top mass, very correlated. I think this is also discussed in one of the previous lectures. And you can see that as soon as you put the Higgs measured mass, how the top mass and W mass also get constrained in the standard model. But still, we have some sort of margin where you can think of keep reducing the uncertainties so that we can try to see if there is any inputs coming from any new physics, which is beyond the standard model. Now, as we continued, as we collected more and more data, we continued like measuring the Higgs boson properties, and even we have already learned it, right, that the Higgs couples to the massive particles, and the couplings are directly proportional to the mass. This is what this particular figure shows, where on x-axis is the particle mass and here is the coupling strength. But even the particles like Higgs to mu mu now have been observed, the candidates have been observed. Minded that I'm using here H mu mu candidate. Given such an event, I can never be sure it is actually the Higgs event or the Z event. We do the statistical analysis of such events which we collect at the end of the day. Okay. So measured Higgs properties are really increasingly consistent with the standard model predictions. So far, so good. But then what is the whole issue? But that's exactly what it comes out to be, that the moment we have a scalar particle in the theory, that means the effect of high masses or energy scales cannot be decoupled. Partly it's coming out because of that there are quantum contributions from the various massive particles to these loop corrections to the Higgs mass itself. And they are quadratically dependent on the whatever the next energy scale which may be available. Now, at the moment, right now, if I talk about that, okay, we are only the electroweak scale, which is of the order of 100 GeV or 200 GeV, then what is the next scale we can think of is when the gravity becomes important, and sort of what we call the Planck scale. So in that case, what happens is that I have observed a Higgs mass of the order of 125 GeV, but my theory is telling me that no, then it's require huge corrections. So then, I mean, the standard model cannot be so right and so wrong at the same time, but it can always be incomplete. And that is the basic idea that we want to start with. Okay. But then standard model is still not the theory of everything, even if like not about the Higgs problem only. There are many things like we discussed just now that the dark matter is not being explained yet. It's a sort of like evidence which is readily available to us experimentally, but we don't know how to explain it. Then understanding the electroweak symmetry breaking, that's an ongoing question and ongoing effort right now. Then there are quite a few like origin of matter, antimatter, then how to incorporate gravity and many such things. And there are several extensions of this standard model that have been proposed. And several of them we also heard from Professor Okada, for example, Z primes and the long-lived particles which are coming from the axion-like particles and all that stuff. Okay. So what is the basic idea? That there are these big questions we talk about, that is the dark matter, the origin of the electroweak symmetry breaking, naturalness, unification of all the forces, origin of matter, then origin of like flavor, that why we have different flavors of these particles, why the different generations, new forces, or some more symmetries to be invoked. So these are the big questions we try to address. And these are the sort of recipes one can think of, that there are different models which are available to us, which we can try to sort of check in the experiments, that how to go about this. So supersymmetry is one of them, then compositeness or extra dimensions can be, there can be extended Higgs sectors. And each of them try to answer many of the questions which are like more popular, these more studied theoretical models like supersymmetry, or it could be addressing some of the issues. So the challenge for us experimentalists then becomes that there are a variety of new physics scenarios Either these predict the new particles, that's what we try to sort of create and try to get an access to them, or they affect the standard model predictions. So the experimental program has to be generic enough to cover as many of as this possible. And that's what like sort of our basic philosophy behind the LSC experiments is. So I will just take one example here, which is I said that, okay, the supersymmetry is one of the most popular one, and like what exactly sort of the features which will come out if we extend the standard model via the supersymmetry. So the key point here is that there is a supersymmetry predicts a duplication of the standard model content. So every fermion has a boson, supersymmetric partner, and vice versa. So we are essentially having these standard model particles, and we have the corresponding supersymmetric field, which are differing in spin by half. So every fermion is a boson here, and every boson is a fermion here. Now, this is the detailed mixing of the electroweak inos, because these are the interaction eigenstates, and then what we are looking for the experimental is mass eigenstates, and there we have some mixing and we get the particles, neutral inos and charge inos. We will come back to this later. But the basic idea here, the main motivation for invoking the supersymmetry is that when these particles contribute to the in the loop to the Higgs boson measurement, Higgs boson mass, they cancel each other. These contributions which are diverging in theory cancel each other. So the Higgs boson mass is one way to stabilize this one. Now, moving ahead. So why the supersymmetry is attractive? So one is that it stabilizes the Higgs boson mass. It gives the relative corrections in a way that divergences are cancelled. But also important point is that if this particle, the lightest neutrino, if it happens to be the lightest supersymmetric particle, it's weakly interacting and neutrino, like neutrino-like in terms of the interactions, then it could be a potentially dark matter candidate. So this was one of the outcome or side effect, I would say, for the supersymmetry models, which made it popular. And then it also provides some sort of, when we say that okay, all the interaction strengths are running as the energy scale, the SUSY, as soon as you invoke the SUSY, they also sort of unify at some point, what we call the gut scale. But the most important point here is that the SUSY extension is a small perturbation, which is consistent with the electroweak precision data. Because we cannot keep invoking something new and really sort of, which really collapses what we know so far. Because all the results are experimentally observed and measured, right? So it has to be consistent with whatever we have measured so far. So that is another like the main sort of for me, which was also an important feature of this supersymmetry. So we can generate all these particles, and how do we go about studying them? So first thing is that how do we create these particles? So that's where our accelerators comes in picture. And we can either accelerate electrons or protons to very high energies and just collide them. So that's what D equals mc square. And at Large Hadron Collider, we are accelerating protons to 6.5 TeV and colliding them at the center of mass energy of 13 TeV. So there are two beams, both at the same energy, collided head on. So this is how the LSC looks like. It's a 27-kilometer ring, 100 meters underground at the borders of the Switzerland and France. And it squeezes the energy into a space which is about like very, very small, like million times smaller than a mosquito to give you the size of it. And the temperatures which are billion times higher, but it's done at the very, very small moment, I mean, the fraction of the second. So this practically creating the conditions of like close to time of the Big Bang, and then you can generate all these particles which are coming out. So we are basically probing the smaller and smaller distances. So this is the difference. I mean, when I talk to my students here, that it comes out that, okay, here you are really tinkering with the nature and trying to see that, okay, what it's trying to tell us. So the way we measure the performance of the accelerators in practically speaking is that how much data we have collected over the time. And this is what we gives us the total integrated luminosity. It's the measure of how much data we have collected. Now the unit it is presented in femtobarn inverse. I think we just multiply with the cross section and you get the number of events which will be available in this much amount of data. That's the basic idea. So if I talk about the processes which are of the order of 1 femtobarn inverse, then in 160 or 100 femtobarn inverse, I will get 100 events. It's really 100 handful of events in that sense. Now we have these two general purpose experiments, CMS and the Atlas here, which are for the SM and BSM studies. The Alice is more targeted towards the quark-gluon plasma studies, and that's mostly about the heavy ion collisions. The CMS and Atlas also collects the data, but the Alice is more optimized for certain studies. The LHCb is more dedicated for the B physics or the flavor physics kind of scenarios. So what is actually happens in the proton-proton collision when we talk about that, if these high energies, it's essentially the interactions between these partons, because we know that the protons are not just like fundamental particles. They are essentially, inside if you see, it's basically 3 valence quarks and then gluons and many of the C quarks, the quark-antiquark pairs. So it's one of these pairs which will collide, and either it's usually these mundane the processes which happen, or it sometimes can create, for example, the dark matter or the SUSY kind of production. But we are colliding the protons every 25 nanoseconds. That is, the collision rate is 40 megahertz. But such processes might be produced 1 in 10 billion events. So the challenge is, how do we identify this handful of collisions out of these billions of collisions? So how do we study these particles? So the general idea is that we have all these massive particles, WZ, top, Higgs, or any SUSY particles or any Z prime. They are all unstable and they will decay. Only the what we call the stable particles are the ones which will traverse through the detector and deposit their signatures after interacting with the detection medium. One thing we have to keep in mind, that whether we are producing a 1 TeV particle or 10 TeV particle, at the end, our electronic signal is coming from just the electrons which are there in the detection medium. So your energy interaction is really happening with the atomic electrons at that level when you are creating an electronic signal. Okay, so whatever particles you are talking about, they have to interact with the detection material, the detectors we talk about, and give us the electronic signature. So this is the generic picture of a HEP detector, which is usually onion-like structure. I will just come back to the details. And then it just layer by layer, it is optimized to really target or see the different particles, to record the signatures from the different particle types. So the CMS, Atlas, LHCb, Alice, they are all using a state-of-art detector technology to identify these particles and measure their position and momentum. So this is the general picture. As I said, this is like layer by layer onion-like structure as it folds as you go away from the interaction vertex. And these are how the Atlas and CMS look like. The LHCb is more suitable, is more optimized for studying the particles which are generated more forward direction. That's where we are talking about the B physics. The Alice, I think it should be, so this is not a 4 pi coverage, while these two are complete coverage around the interaction vertex. The Alice also does not have a 4 pi coverage, it's only the half side of it. But we will focus on the CMS and Atlas for now. So this is how the CMS detector looks like. Here is the interaction vertex. It's immediately followed by the silicon pixel detector, which is like really a granular detector, so that you can really see particles passing through it, the charged particles, and can really reconstruct the tracks and go back where the interaction happened, at what point in the space. And it is followed then by the calorimeters. So basically it's the electrometric calorimeter. So these are the silicon-based microstrips. And the calorimeter is the homogeneous calorimeter made up of the lead tungstate crystals. So the electrons and positrons passing through, they just deposit their energy in this calorimeter. This one is then followed by the hadron calorimeter, which is more tuned for the charged and neutral hadrons, like the neutrons and the charged pions or protons produced in the interactions. And then it is followed by a magnetic field coil, which provides us the 4 Tesla magnetic field, and then the muon chambers, which are more of the gaseous detectors. They are more based on the drift tube technologies or the resistive plate technologies. And overall, they really come out to be like more than 1 million channels, so individual readouts. So this is how it looks like practically. So if I take a slice vertically, and this is how it looks like here, and I'm taking further slice of this one, that here my interaction happened, particles were produced in the interaction, PP interaction. And then all the charged particles pass through and they leave a sort of hits in these tracker layers because they are one after the other. So you can trace the particle where it is going through. And then it passes through the calorimeters, and then it goes to the particles which survive, they go through the muon chambers. So it's basically, if you see here, when we are talking about this tracking, the particle trajectory should not be disturbed. So we want to have the minimum material there, highly granular, so that we can differentiate this high density of the particles coming out at closest to the vertex. So this is what the silicon one is, the tracker is. But for the calorimeters, they really measure by stopping the particle completely, or sort of a destructive measurement. Because these particles, electrons or hadrons, they will shower. They will create the shower of the particles, and that's what the chunk of energy we measure trying to sort of check whether there's an associated track or not. And then we say whether it's a photon here and it's an electron here. Similarly, this could be a neutron here, and this is sort of a charged pion here. Muons pass through all the way and really give this signature, because the muons don't bend, so they don't create the electromagnetic shower here, and they just fly by, only depositing energy by signal by the ionization processes, and that's how we trace them. Now, the neutrinos, or if this supersymmetric, for example, neutralinos, they are weakly interacting neutral particles and they don't deposit any energy here. So we infer their presence by some other means, by looking at the event as a whole, and that I will come back to in a couple of slides. Now, I think I talked about the stable particles, but I did not talk about the quarks and gluons, which are really the products of all these proton-proton collisions. So what happens is that the quarks and gluons immediately hadronize. They become a collimated display of what we call the colorless hadrons, which is essentially charged pions and pions and protons and neutrons. They're essentially dominated by the pi plus, pi minus, and pi zeros, 1/3 of each. So this is what happens, that we have the interaction, the quarks really or gluon just come out and they immediately hadronize. And what we see in the detector is essentially these hadrons. Okay, the pi zero, the lifetime is very small, it's 10 to the minus 16 seconds or so. And so it immediately converts to 2 photons. So that's where that photons come from. So I can go back and actually from these techniques of identifying the particle types, is what we call the particle flow, that we can really sort of combine the information from the different subdetectors and see that, okay, what kind of particles we are producing. We can actually see in the jet what is the composition. So this is the experimental output, not just the taking from the generators and identifying the particles. So here we can sort of say that, okay, this red one is essentially here the charge hadrons contribution in a jet, which is of the, I think, as a function of the jet PT in the central region of the detector. And you can see that, okay, how many charged pions we have, then how many neutral pions we have. The photons is nothing but the pi zero going to 2 photons. And then there are these neutral hadrons and some other particles which might come out. So for the accurate measurement of the jets here, which are our discovery tools in some sense, because it's a hadronic collider, the key is to understand the response of calorimeters and all other detectors to individual particles, what we talked about here, which constitute the jets. And by themselves also, because W will decay, for example, to leptons, the lepton and neutrino, or for the Z will decay to 2 leptons. So we have to really understand our detector as much as possible and calibrate it properly. So that controlling its response and resolution and maintaining its performance is the key for the success for any of these experimental program. And why I'm emphasizing on this, I will come to this topic in a couple of minutes. Now, jets are furthermore important tools, because what happens that even if you have a top quark, it can be highly boosted and it can really sort of decay in a way that all its products are really collimated. So you can't differentiate them separately. So if the top was at rest, probably, or not so boosted, we will have these 3 jets coming out, W going to QQ bar, and there is a B jet. But if the W is too boosted, then these might merge into single jet. So this is what we do is that this particular cone, which we decide that what should be the area of the jet, we have to really optimize that we don't cover too much of noise. At the same time, get the maximum signal. For these kind of signatures, we might have to widen up that area. This is what we call the large area jets. And if the top is furthermore boosted, then we can have all these decay products in just one cone. So this is an excellent tool which has come across, like given the large amount of data and large amount of boost available at the LHC energies. This is becoming what I will talk about it in my next slides, that the processes which could not have studied otherwise with the boost tags, we can really do it. For example, for the neutralino searches in the SUSY. So this is what, and this one has been much improved by the advanced machine learning techniques. For example, I just gave you an example and the reference, if somebody wants to go and check it, that many of these DNA-based searches which can combine the information from both the merged one, semi-merged one, or fully merged one, and try to tag whether there was a top in the event or a W or Z or H. Okay. The another important from the jet side is to tag the jets original from the B quarks. This is an interesting one because a lot of new physics really favors the 3rd generation particles, and the bottom quark becomes one of them. And also the top always decayed to a B quark, right? So tagging a B is important even to tag the top quark events. So here you can see that here again, we are using some sort of the deep neural networks. And here you can see that how the efficiency can be compared with the different algorithms. And then we have picked up one of them. But there is one more important point here, that there are scenarios where the mother particle and the daughter particle here, for example, here I am saying the SUSY top particle and the neutralino, they can be so compressed or close in mass that the B can be very soft. If that is the case, then we have to apply the special algorithms, and that's what we do when we are in the compressed spectrum. So the reason to point it out explicitly here is that if we want to cover all kinds of scenarios which may exist, and that's our responsibility as the experimentalist, that you have to churn the data as much as possible. We have to go via all these tools and figure out where are the loopholes and cover them up. So we develop these special techniques for sometimes very small corners also. Now, how the neutrinos and the neutralinos will deposit or convey their presence is essentially what we call the missing transverse momentum. The idea here is that the proton-proton collisions are, the protons are accelerating in one direction. So let's call it the Z direction. So initially there was no momentum in the initial direction, and we don't expect anything in final direction also. So it's just the momentum conservation in direction perpendicular to the beam direction. And if there is anything which is not zero, that means something has passed through, some energy has been missed out. That's what we call the missing transverse momentum or missing energy, missing transverse energy. But if there is any issue with any of the detector components, it can still give you the, if there is something not measured or something over measured, then also it will give you the imbalance. So we have to be super careful to clean up our data against these detector issues. Otherwise, we will be claiming supersymmetry or dark matter or something new every next day. Okay. So these are more or less on the tools. I would like to point out a couple of more challenges here is that when we talk about the PP collisions, it's basically, we already said it, like it's a nutshell, it's like the two bunches coming out, and each of the bunches like 10 to the power of 11 protons, and then some interaction happen between the two particles. But when the bunches are crossing, there can be multiple interactions happening. Okay, that's what we call the pileup. What we see in the detector is something like this, that all the particles coming out. How many interactions happens, we have to sort of infer from the data we are seeing. Okay, so this is what happens, that every year we had more data being collected in the same time span of, I mean, whatever the runtime is in a given year. And you can see that number of interactions which are happening in per bunch crossing. So basically one such instance, this one is essentially increasing on an average for every year. Now, two issues which happen here is that we have to maintain the efficiency, resolution, response of all the objects I described earlier. The electrons, photons, all the charged particles, vicinity, and everything, if we want to maintain our physics performance for all the measurements and the discoveries. But at the same time, the detector is not a dead material. It's essentially a living being in the sense that it is exposed to the very, very high radiation levels, especially the detector components which are in the direction of the beam, where the particle density is too high. There, the challenges are further high, because you can see here in the electromagnetic calorimeter, the last part, the transparency has decreased like this, and we are really running at the very low transparency. Now, we don't use the electrons and photons from that region anyway, but that becomes important for the missingness, the missing transverse momentum. So we really have to constantly keep calibrating it and try to see that, okay, we can maintain the performance as really needed. And this is one of the reasons that we have to replace these detectors for the high luminosity phase of the LHC. Now, we are the reason why I said the resolution and all the objects are important is also because of the trigger. So this you can see here in this plot, the various processes and as a function of the energy. So we have to focus on this line, the LHC one, that how the different processes have the cross section. So it's dominated by essentially the QCD processes, QV interactions. The high PT ones, the cross section size small, and this is the order of magnitude here covers like almost like 15, 16 orders of magnitude. The Higgs and new physics and something like here. So what is happening here is that we are getting enormous data rates, while our the actual writing part on the tape is of the order of 100 Hertz. We cannot write, so we are really throwing away 99% of the data, 99.99% of the data. Okay, so there is no going back. We have to really trigger online, look at quickly what the collision has happened and what the processes that has happened, and save that event. Okay, and this part is important, that there is no going back. So that's why we have this state-of-art trigger system where we have two levels. The collisions are happening at 40 megahertz, then it is reduced to 100 kilohertz, and then we try to titrate the tape of the order of 500 hertz. So the LHC experiments, even after all this reduction, is recording 50 to 60 petabyte data every year. or maybe 4 now. So now let's, these are the tools part and technical part. Now let's come to the physics measurements. So let's start with some of the standard model ones. Now, I said that, okay, Higgs boson was discovered in last 1 decade, has been going on and really studying its properties very, very carefully. They figured, so these are the various processes, the modes where the Higgs can be produced. Like, for example, this is the going via the VBF channel or the gluon-gluon fusion or the associated production with a Z or W quark or a TTH production and things like that. The Higgs branching fraction, once the mass is known to us, it's coupling to the various particles, and hence the branching fraction is also known to us. So basically, which particles it will decay to, the rates are known to us. Okay, and so first, one of the first key component here is the measurement of the Higgs mass, because as I said, it's a very important property which we need to know to understand the stability of the vacuum also. And then it's coupling to the variety of the particles, and we have done up to the muons and even the BB. And this is one is very interesting because it's a non-trivial one. I will get back to in my next slide. Now, the Higgs BB, the reason I said it's very difficult one, because as you can see that the HBB is the highest branching fraction, but it is dominated by the QCD backgrounds. Okay, because it's the strong production of the background and the rates are way too high. So you can see in the plot here that the data is the dotted ones, and this one is the multi-jet, the processes, which is the background, and then there's the contribution from the top or the Z or the W. And you can see that the Higgs we are interested in HBB is lying somewhere here. But with the associated production, which is essentially the ZH here, because you can tag the Z as the dilepton event and look at the BB on the other side. And if it is boosted one, we can sort of really, this is one place where the boosted techniques have helped us a lot. That even such challenging processes can be now studied properly. And then the rare process one, for example, TTH, the cross sections are very low. So you can see here, this one shows as a function of the Higgs mass, somewhere here is 125, that what the TTH cross section will look like, and it will be somewhere here. And this is on the log scale. So these are the very rare processes, and still with the the two plots here I show is these kind of searches. In the TTH is very interesting because it gives you a variety of final state. It can be a single lepton, multi-lepton, same sign dilepton, and a lot of these, and each of these we try to study in different final states, because that give us a good signal to background reduction, the separation. So this one, for example, is the TTH with 3 leptons with no taus, but this one has the taus involved, and you can see how the backgrounds are changing, how the signal here, the signal is the red one from the TTH, and here the signal to noise will be very bad. So in this way, we have really sort of tried to study that what is the signal strength, and it is more or less consistent with the standard model. And then also that this was essentially the claiming the discovery that we have seen 5 sigma away evidence of the TTH. Now, the top quark measurements are again important, and its mass is very important to understand the electroweak stability overall. So these measurements are still going on, and now we have the best measurements available, the combined ones. And the plot here shown is the overall result from the LHC as a different center of mass energies where the top mass has been measured. And you can see it is almost consistent with the theory within the given uncertainties, either experimental or theoretical. And similarly, the different processes which involve the TTV kind of, where the TT bar pair is produced with an associated vector boson, which could even be Higgs now, which we discussed earlier. They are also being continuously measured. And more than that, we have also tried to measure the differential cross section. So for example, this is a sort of measurement as the cross section measurement as a function of the PT of the top pair. Okay, and this is another stringent test for the standard model, because we are not now measuring only about the overall cross section, but also the cross section, how it looks like from the different variables. So that can really give us hint to some BSM or the non-standard model contributions, or question the put the standard model in question if something is not matching, or try to improve our tools, the generators, the Monte Carlo, and all that. So this is more like, I mean, what I call celebrating the success of standard model, that we have made so many measurements. It's basically W plus jets and Z plus jets, not only inclusive, but as a function of the number of jets also. That's what these different bullets look like here. Then the diboson production, triboson productions, which essentially tells us more about their self-couplings and all. then the VBF and the vector boson scattering and the vector boson fusion production. But the top quark and Higgs quark, we have made all kind of these various combinations also being, which are very rare processes. And within the given uncertainties and current tools available, I think they're more or less consistent with the standard model predictions. So essentially the standard model survives very well so far. Although we have some hints from the other experiments like the G-2 and the lepton flavor violation results from the LHCb. But those studies are just put such that, okay, we have to continue for the new physics searches. I need to know how I'm doing with time.
So we are currently at 11. So we started what? We started 10 minutes. 10:10, right? So 10 minutes.
Okay.
Oh no, we started 11. Sorry, 10:20. So like 20
That's
minutes.
fine. So there is no rush. I mean, that's what I can see. Yeah. So this practically covers the tools and establishes that we understand our detector very well, and we understand the data very well, and we have made so many measurements which have been either updated with respect to what we already know, or the new ones have been added. So let's go to the new physics searches now. So the issue with the which I generally feel that BSM searches is that, okay, which direction do you want to go for? Because it's such a like sort of a desert that we just don't know that what is the right corner or not. So we have to cover all the corners as much as possible. Okay, and as I commented earlier also that we just see the collision happened. We can see that, okay, some particles came out. I can see it's a missing AT. Okay, that I know from my measurements and my detector tells me. But is this because of a supersymmetry particle? Is it because of a dark matter particle? Is it because of the neutrinos coming out from the Z decay? We just don't know about that part. Okay, so what we have to do, we essentially do the statistical analysis of the data we collect. We figure out what final states we are looking for, and we collect the events based on those final states, and then try to see where we stand with respect to the standard model would have given us, and if there is any sort of deviation from the standard model. So there are two ways to do it. One is that search for the resonances. So frankly speaking, this is how it was for the Higgs one, right? That we looked for the peak around either a sharply falling background, or it was more of a flat bed. Or it can be the non-resonant new physics, where you will see some sort of a broad distribution. Or it can be you're looking for the different sort of signatures, for example, the missing transverse momentum, which can be a signature for the dark matter, and try to see in the tails of the distribution which we expect from this standard model. So this is one example here from one of the supersymmetry searches, where the solid histograms show how the standard model will predict in the given event selection or the given sample of the events, and how the new physics or the SUSY will look like if it happened, or the dark matter could have been appeared, but what my data tells me, which is consistent with the standard model. Okay, so once we have this, so basically we have our event sample selected. We try to make a choice. We take a small sample, and then we try to see that we find how it behaves with respect to the standard model. What are my standard model backgrounds? And then we see the given data we observe and the given uncertainties on the background predictions. What is the maximum limit when new physics can be hidden? That's what we call the exclusion, the upper limits on the cross sections, production cross sections. So I again continue with the SUSY example, because this is one which gives a lot of models, and sort of one can find any favorite channel one wants to look for. So when we talk about supersymmetry, then the question becomes what kind of supersymmetry model we want to look for. Because as I said, that supersymmetry predicts the duplication of all these standard model particles, and hence all the couplings, masses, and everything becomes free parameters which we have to observe or measure in the from the data. They have to be experimented and measured. So with these many parameters, we can have any like variety of models, and we know that it's a broken symmetry. It's because we haven't seen any scalar electron, which is counterpart of our standard model electron. So the masses are like sort of heavier than what we observed in the what are the corresponding standard model particles. So we have a sort of variety of models which can be available. So one of them is essentially what we call the R-parity conserving minimal supersymmetric extension of the standard model. In this case, the neutralino is the lattice supersymmetry particle, and experimental signature is the missing AT. And then there can be a lot of other particles, the jets and the leptons and everything. There could be scenarios where the gravitino is the LSP. So neutralino is the next to an LSP particle, but not the LSP. And here also the signature will be missing ET, but there can be many other, either it can be dominated by the photons, or it can be Higgs, or it can be W or Z particles in the final states. There could be R parity volatility scenarios in which there is no sort of stable LSP, and then we can have no missing ET signature, but a lot of jets in the final state. So here it becomes all the more difficult that how do you differentiate your signal from the QCD background, the multi-jet background, basically jets all over. Okay, and there can be then a stealth scenario which can invoke a stealth sector with one or more different siglets, and there is again no missing transverse energy or very low missing transverse energy, but again a lot of jets. So we want to cover as many final states as possible. This is just sort of one example that if I really talk about only gluino pair production, so everywhere I have the gluino, but depending upon what exactly the model and underlying assumptions are, and what are the particles involved in the decay chains, we can have this variety of possibilities, just as a simple example. There can be number of jets, 0 leptons, more leptons, photons, missing ET, or it can be no missing ET signature. Okay. And when I say that, okay, the variety of possibilities, basic to simplify that, just to visualize, is essentially that we have different particles involved, and depending upon what their mass hierarchy is, we can get different final states. And the cross-section comes in picture only for the production, that which one will be dominated. So if we really think that way, the first searches to come out are essentially the strong production because they have the maximum cross-section, while the electroweak ones are the lower cross-section, and that takes like more data required and more scrutiny required. So we try to have the search program, which is, okay. Now, before I move ahead, just a small comment here that we try to look for the simplified models. The term which I say is that we sort of try to use this information or this knowledge that, okay, there are too many possibilities, and we have to pick up something to figure out what kind of events we want to select. We call them simplified models. What we do is that we pick up some choice, for example, this one, and try to call it a simplified model and try to see that, okay, fine. In the particular channel we are looking at, only these particles are involved, and we don't care for what other particles are doing. So that's what we sort of use. So when I say these, all these are the simplified model scenarios. So that when I say here the gluinos going to the QQR pair and LSP, I say that all my S quarks are very heavy, they cannot be produced at LHC. But this is mainly for simplification and the presentation of the results. That doesn't mean that, okay, we can really bias our analysis just based on this one particular channel. So we try to sort of base our searches on the final states. And here is an example that you have the 4 tops in the final state, which means you can have from the top decays, the various combinations. You can have either 0 lepton final state, which is like 32% of the events. It can be 1 lepton, which can be 40%. And then the 2 leptons, which can be opposite sign, same sign, or 3 leptons. Now, the reason I want to point out this one is like here. So the first graph here is showing the number of jets for the 0 lepton scenarios. And here you can see the dominant background, the standard model process is the Z2 invisible processes. There is no other lepton. So we have sort of got rid of the lost lepton and the TT bar and the W jets maximally. Whatever lost the events are surviving from that is because the lepton inefficiencies. But if you look for the 1 lepton here and look at the transverse mass between the lepton and the missing ET, then you can see here is the TT bar is the dominant background now. So, and then it is for the multi-leptons that it can be the fake leptons or the non-prop leptons, mostly coming either from the conversions or the B decays. It's essentially the biggest background here. So dividing our sample in this way, what we are trying to do is that we are trying to increase the signal to background ratio, so basically the sensitivity, but also making complementary searches from the same data. So later on, if you see signature in 0 lepton, we always have something complementary going on, which is orthogonal to this. These events are not same, they are separate event samples. So whatever events coming in here won't come here. We also have the complementarity to understand what exactly is going on and we characterize if we see any new signature. So that are the key points. Now, when we go about the searches, we also decide what kind of kinematic variables we want to look into, how we want to select our events, for example. So for the 0 lepton events, where QCD is the dominant one, we just try to go for the missing ET. That is the most sensitive variable. But there can be other variables also which try to make use of, like, kill the QCD. So there is a variable called alpha T, which puts the QCD all on the lower side, and then we have the signature which is on the higher tail of it. Similarly, for the single lepton, that's the delta phi between the lepton and the W boson. And here you can see that, okay, the signal will lie on the higher side of the higher values of this variable. And similarly for the 1 lepton and 2 lepton. So what we do is that we try to come up with the kinetic variables which can give us the good separation between the signal and the Standard Model backgrounds in some phase space. So if I look at it inclusively, I will not get that much of signal significance. But if I really divide this sample into statistically exclusive search regions, I can easily get good signal to background. Okay. Now moving ahead, so suppose we pick up the electroweak SUSY production, which I said that is the lowest cross sections, and hence now the current searches are essentially coming out in the electroweak sector. The Gluino searches have already been done, I think almost 2 years ago, most of them. A few are coming out, but right now the focus is more on the electroweak ENOS. So here that I said that, okay, fine, these particles mix, and ultimately what we get is the charge ENOS and the neutral ENOS, and what we are looking for is their pair production. Now, these involved a lot of via these leptons, the leptonic channels, or it could be without leptons, and these leptons are way too heavy, then it directly decays to the Z or W particles and the neutral ENOS. So until now, the idea was that these searches were dominated by the leptonic final states, because that's where we get the maximum background rejection. But with the increasing reach, with the higher energies, with the LHC, which is 13 TeV now, and the large data set, we are also getting a lot of boosted particles. So if the W or Z is boosted, if they are very high PT, if their mass difference between the NLSP and LSP is very high, these can be boosted and we can tag them as the jets. Okay, and so then we can really benefit from the large branching fraction of the Z and W to hadronic channels. So W goes to like 2/3 times to the QQ bar prime pair. So, and also what happens is that if these are very compressed, then we will get the soft leptons. So now the way we try to cover these is that we try to have the generic analysis. So this one is, for example, just a multi-lepton search, and try to cover in, for example, the 13 combinations of the final states. There can be 2 leptons, there can be 2 same sign leptons, opposite sign leptons, consistent with the Z boson or not. It can have taus or not. It can have 3 leptons. And so this is what we try to cover, that as much phase space as possible where I can have the multi-leptons, 2 or more leptons. Okay, and you can see here that this can really cover the models with the light leptons, where it can be NLSP, the neutral ENO2 going via the the lepton and then ending up the too many leptons, or it can be via, when the leptons are not accessible, it can directly go to Z and neutral ENO, or there can be graviton LSPs. Now, using these kind of different channels, we can really target many of these scenarios in just one analysis. So you really go over, and the full space you try to scan that, do I see something which is beyond the standard model? And so far we haven't. It's all consistent with the data is consistent with the standard model predictions. So this is how it finally looks like, that we have so many search regions which are further divided into the to enhance the sensitivity in Missing-ET or the number of jets, B jets or not B jets. And these are the final results in all those search bins, which are statistically combined to see whether which models are excluded or not excluded. So combining these search regions is essentially what we get in these different models, that we can exclude up to 1.1 TeV neutral ENOS in certain the tau enriched scenarios, or the WZ mediated, it is of the order of 600. But if it is WH mediated, the limits are much weaker. We don't go up to more than 300, 400 GeV particles. So such generic analysis might not cover the full phase space, and then we have to go for the targeted ones. And that's where we benefit from what I said about the boosted jets. So here we go with this one, the same model. Here, this model did not have much sensitivity because of the multi-lepton generic analysis. But if you look for the WNH or Z bosons in boosted jets and look at their mass, so you can see that the signal stands out against the background nicely. Okay, so then we sort of go back and do our search in these variables using these tools. So this is a 0 lepton search now, no leptons required. And what we do is that we try to tag these, either you have the B jet in the final state or not, depend on whether the H or Z are there or not. And then you can see here that we can actually extend these searches from the 200, 300 GeV in these models to really 700, 800 or up to 1 TeV masses. And this is the similar analysis done also in the single lepton channel, which I have not covered, but I just showed the results here for the completeness. So even for the Vino-Vino scenarios, we can really sort of go to the up to 1 TeV particles. So what I'm trying to emphasize here, that if I go only for the target searches, we lose out a lot of phase space. If we go only for the generic phase space, we may lose out the particular corners. So both are important. And similarly, this was done for like when we have further low cross-section scenarios, but so Higgs is already becoming a new physics tool for us, and it's really appropriate to the new physics scenarios. And this is one example where we don't look at the boost, but we also look at the really low PT ones where the decay products are not merged, they are not boosted enough. But then we try to combine with the variety of these neural network techniques and try to get the results. And you can see here how the signal looks like in this against this huge background. And we are using the this neural net techniques, we can really separate out the signal from the standard model backgrounds. And these are the final results, and no good news so far. But you can also see this whether the standard model survives even in the tough corners without any issues. So this is one example with the soft leptons where what we have is the neutralino and this mass difference is very low. In that case, what happens, the missing area is very small. And we have the soft leptons. The lepton PT is very small, so the backgrounds will be high. In these scenarios, what we do is that we try to get one initial state radiation, which can be a very high PT jet. So the whole system is boosted against this, and we get the high vicinity. And this is a similar technique also used for the dark matter searches, which I have not covered completely here. But the idea is same, that you can have the dark matter particle produced, but you can't see them if they're back to back and all. You have an ISR tag, which is a visible particle, which could be what we call the mono X searches. It could be a jet, it could be a monophoton, it could be a mono Z, it could be a mono W. And we try to look for the high missingity in the as a function of the different variables. Here the example is for the MLL dynamic mass, because the particles in the final state involve the 2 or 3 leptons.
There is 4 minutes left. Thank you.
Yeah, so this is the final results. That the point which I want to make here again is that depending upon the mass differences between the different particles and what mass spectra you are considering, the sensitivity of the given analysis might be different. So it's very important that when I say that, okay, this analysis can cover this much, or this model is completely ruled out, we can say model ruled out. We cannot say that, okay, supersymmetry is ruled out, or the or the particular dark matter is ruled out, or something like that. We have to be very careful when we look at the interpretation of these models and these results. So this is the summary for the electroweak. I already summarized this, that the magenta one here was for the generic search, and these have been further extended with the new tools we have developed with the boosted jets. And this one, for example, shows that this corner would not have been done if there were no soft lepton techniques which we were using. So we try to have a complementarity in our searches and the measurements. This one I will skip, and this is the status of the gluinos that we have excluded, for example, up to 2 TeV particles, 2 to 3 TeV particles. Now, similar things go for the variety of other models, for example, the leptoquarks, which can help us in understanding if there is any transition between the leptons and the quarks. And here also, we can have the final states, which can be leptons. And this one got a revised interest because of this lepton flavor violation results from the LHCb. That some of these could be an answer if the leptoquarks exist. Some of them can answer those anomalies. And here also, depending upon what kind of model you assume and what kind of couplings you assume, the reach or the exclusion might be weaker or higher. So this is the general summary of the leptoquarks, and you can see that we cover all kinds of final states, including the 3rd generations or the 1st generations. Yeah, so I think I can stop here. The way forward is that this is the, let's say, near future. Right now, we are around here, and then we are about to start the run 3, which this will be slightly shifting by a year or 2, which might be extending the run 3 and slightly moving away the LS3 by a year or so. And the idea is that we can really sort of control the lot of, so this is the projection of the uncertainties on these parameters with the 300 femto1 inverse, which will be end of the run 3, and the HLLHC1. So this is the scenario I'm talking about. This is the phase of the high luminosity LHC for the 10 years, where we will collect 10 times more data than what we have collected now, and we'll collect by the end of the next 3-4 years. And we can also sort of probe a lot more mass states for these rare processes or for the compressive spectra also. So you can see here that the reach for the very heavy particles will not increase much, but for the rare processes, it will really be a big chunk. So just to summarize that the standard model has been surviving well in all corners of the phase space, except the anomalies which have been reported by the LHCb and the G-2 results, etc. Even though there are no hints, yet the motivation for the VSM remains as strong as ever. So there's an urgency to understand the stability of Higgs mass, also the LHC dark matter, or any other question you may have. The LHC performance has been fantastic, and the CMSN results, ATLAS results are still coming out. And we look forward to the run 3 as well as to the HLLHC. I think there are a lot of opportunities there, and that's where I stop. Thank you for listening.
Thank you very much, Professor Sharma. So let me look at the chat. So far, I do not see any questions. If there are any questions, you can just unmute yourself and you can ask directly. I think that's one option we can do.
Hi. So I have some question.
Yep.
So yeah. So the first one I want to ask is, how can experimentalists use LHC data to investigate dark matter? I mean that we can detect dark matter, right? So what signature we are looking for the
missing transverse energy. So this is what we talked about here. It's essentially, it will be the same for this technique. It's essentially for the dark matter also, because this literally could be a dark matter candidate, right? So you can produce a dark matter candidates. We look for one very boosted object and look for the missing transverse momentum.
So you
the
mean
dark matter candidates will not interact with the detector material. So it will just fly through. We look for the missing transverse momentum.
So you mean like we're looking for the radiation of that signal, and
we look for, yeah, so we look for something like this, that if something happened, one interaction happened, I get all my particles, right? But there is something imbalance in the final state particles. So I take all the particles, take their vector sum, the momenta. Ideally, it should be 0 because the event has to be balanced, just the momentum conservation. If there is some imbalance, that is a signature of the dark matter candidate or the neutrinos.
And my second question is, when you perform the cut, like the kinematic cut for PT, for pseudo-gravity, how can you choose the cuts, and why do you choose this cut for your analysis?
Yeah, so that is again to look for essentially that how do you increase. Okay, let me put it this way. I can show you one example here. Yeah, so for example, this one. So this I'm doing for the missing transverse momentum. It could be any other variable here. Okay, so if I see this example here, any of these examples, for example here, if I take this as an inclusive sample, so just I count the number of events in the data total and total number of backgrounds, versus I slice this in the different bits, right? So if I look at only this much, for example, all the events above missing transverse momentum 600, the possibility of my signal lying there above the background is higher. So this is just the signal to noise rejection, signal to noise improvement. Okay, so it's just like improving the sensitivity of these analysis.
Yeah. Thank you very much.
You're welcome.
Any other questions? So I have one question. So the program to implement the machine learning for the high luminosity LHC, how comprehensive is that going to be? How much of that is going to be like a machine learning now at this stage? Yes,
so I think this, okay. So far, we have been using machine learning more for the object tagging, and now the various analyses are coming out which are using for the event classification also. But I think the machine learning is going to be, I think, more used. So for example, I'm myself working on this high granularity calorimeter. And the amount of granularity we have there as compared to the current calorimeter, I think machine learning does wonders, I would say. So I think what we are trying to have is that we will go for the machine learning also at the reconstruction level. So at the detector reconstruction level, and perhaps at the trigger level also, because a lot of the trigger is going to be re-implemented, right? And we will go more towards the FPGA based techniques.
Nice.
So perhaps some of those things can be applied. So those are like, there is an interest and people are already working on it, surely.
I see. So those projections that we had, like LHC had before for high luminosity LHC, do they have the machine learning part implemented, or do we we expect more? So we expect more improved from machine learning.
Yeah.
How much typically that you expect? Like how much improvement a typical machine learning, or does it depend? I guess.
Yeah, I was about to say that. Okay, it depends upon which kind of corners you are looking for, right? If you already have very high missing ET and you're already dominated by the statistical uncertainties, then we are not going to gain much.
Okay.
But if it is somewhat at the borderline of being on bulk or more towards the bulk where the backgrounds are high, that can really sort of help out.
Yeah, I see.
So for example, even like the techniques like normalizing flow and all are catching up for the EFT parameter extraction, for example. Right, I think those all will be extended for the searches also.
Okay. Okay. So we have another question from in the chat. Avi, do you want to ask the question yourself? Okay, I can read the question. So he wants to know, can you briefly discuss the techniques to tag boosted objects?
Yeah. So the starting point is this, that quarks and gluons, they hadronize. And what we get is essentially a spray of particles. In the detector, you will just see some cells lighting up. Okay. Now, what happens is that suppose there is a top quark which is produced, it will decay to immediately to W and B quark, and the W boson will further decay to QQ bar prime. So the two quarks here. So now you have three quarks in the final state, and they will all hadronize. You don't see them isolated and separated out. All we see is their signature. So this is this cartoon here. Each of them is a jet. So each of them is essentially these four cones I'm showing here is one of them, either a quark or a gluon. Okay. But now what happens, if the W is very boosted, its PT is very high, then the opening angle of the decay products is small. So then these two jets might not be separate, they might merge. And this is what I'm showing here pictorially in this cone. Okay. And then if the top is further boosted, it might happen that three of such jets can be merged. They might not be showing them separately like what is shown in this cartoon upper here. Okay. So now what we go is that we cluster all these particles or the detector cells or the particle flow detector level particles we have get. And we try to look at internally at their substructure that what this jet is telling me. Okay, is it some sort of like what I expect from the the QCD multijet, those kind of scenarios, or there are three small chunks there, which I try to identify. So you can look at the jet mass. You can look at if there are any substructures inside when you try to sort of clean it up and see that, okay, am I seeing three different blobs, or it is just one jet? Or it is sort of a B quark, which can be sort of a displaced vertex also. Now, one is that you can really look at it manually. That's how we started with at the beginning of LHC. Try to see that, okay, what the substructures are. Or you can use all these inputs to your machine learning algorithm and try to train the network that whether we see some features against the QCD, the quark gluon jets or not. That is the basic idea. Is this what the question you were trying to ask?
I think that was Abhi. Yeah.
Abhi, yeah. Abhi, does that answer your question?
Yeah.
Okay, cool.
Yeah. Any other questions? Maybe one quick question at the end.
Yeah, so just a comment to Abhi that starting point is that you just go and manually check it, but then the question becomes that how to improve the purity and the efficiencies. That's all the fight becomes about.
Okay. Again, I'd like to thank Professor Sharma for a very nice talk. And I
Thank
think
you, everyone.
we want to formally end the event for today, and I hope to see everyone tomorrow. So we have that social time tomorrow, so please join us so you can ask questions regarding physics, like your particle physics in general, as well as particular physics topic questions. So please join, and we'll see you tomorrow. Thank you very much, everyone.
Thanks, everyone. Bye.
Bye.